Okay, everyone. So we're going to start looking at the final point in terms of colligative properties. And here it's about now, we've spoken a lot about, so if you dissolve a compound, and we've kind of treated all compounds relatively the same up until now. So whether or not it's been a protein or a single molecule, we haven't really looked at it being differently. But let's quickly talk about perhaps how could it affect your colligative properties in a different manner. So let's say you have something like chloroform, so CHCl3 liquid, and you want to dissolve that in water. Then, of course, this is a organic compound, molecular compound, so it's not going to split up into anything. You should expect it just to dissolve in the water. So meaning you have one molecule here on the left and one molecule on the right. So meaning you have, if you dissolve 1 mole of molecule, of 1 mole of liquid molecule, you're going to get 1 mole of aqueous molecule on the right. But what happens if you compare that with, say, something like sodium chloride, and you dissolve that in water? What do you get on the right here? Well, you get sodium chloride aqueous, or sodium ion aqueous plus chlorine minus aqueous. Okay. And immediately you should notice, well, okay, that means we're here taking 1 mole of something, and on this side we get 2 mole ions, right? And inherently in all of these colligative properties, we've constantly spoken about, well, if we dissolve a compound, it's going to have some effect because we look at the concentration and it dictates by how much it affects the properties of it, and how much of this thing is dissolved is going to affect the properties of it. So perhaps it's also useful to look at, if something splits up into 2 or 3 or 4 or 5 fragments, does that have an effect? So meaning, if something only is 1 fragment, so meaning it's just a molecule, it's a molecular compound, versus if it can split into ions, so meaning for every 1 mole that you dissolve, you technically get 2 mole of ions or 3 mole of ions. Is it the case that you might get 3 times the effect or 2 times the effect for dissolving sodium chloride, whereas you would have gotten only 1 time the effect for dissolving chloroform? Right, that kind of makes sense where I'm heading with this argument. Right, and it turns out, if you look at some experimental results, that if you were to look at, say, sodium chloride and sodium sulfate. So let's quickly remind ourselves of both of these. Sodium chloride splits, of course, into sodium and chlorine minus, and sodium sulfate splits into 2 sodium plus SO4 2 minus. And if we were to calculate the freezing point just in a normal manner, so we take the KFP and we multiply it by the molality of several number of solutions. So what we do is we make up a bunch of solutions of the same concentrations, right? And we calculate based on the KFP that we have measured, we calculate what it is, right? So these are the calculated values. We go ahead and we calculate what it is. But then we also go to the lab and we go and measure what it actually is for those concentrations. And what you then see is, for every time, or for in every situation, if you take the measured value, so meaning this value here, and you divide it by this calculated value. In the case of sodium chloride, we are out by a factor of roughly 2. And if you look at the sodium sulfate, we're out by a factor of around 3. So look, I mean, they're not exactly 3 and 2, but you can see that there is some sort of effect here. So meaning we cannot just model these as molecular compounds. We have to kind of look at the fact that there are 2 ions and 3 ions in solution here, because clearly if we measure the change in the freezing point versus just calculating them as molecular compounds, we underestimate the change by 2, which is actually exactly the number of ions. And in this case, we underestimate by 3, which is exactly the number of ions. You might argue that, well, 2.26 and 1.83, you'll notice that as we calculate, we start decreasing the number. And that is that this law that I'm going to introduce now does not hold by when the concentrations at high concentrations. It works very well at dilute concentrations. But anyway, so let's get to the law. So, like I say, what's going on? So one person that introduced something was Van Hoff, and it's called the Van Hoff factor. He said, well, what we should do is we should actually write our colligative property measurements as such. So maybe I should just highlight the important thing. We should introduce this Van Hoff factor. So meaning if you have a compound that splits up into ions or components, then you should multiply whatever your normal factor is, so KFP times M, and then you need to multiply it with however many components it splits up. So for sodium chloride, that would be 2 ions. And for sodium sulfate, that would be 3, because they have 3 ions. So then the I is 3 and 2. And how many ever ions it splits up. And Van Hoff then said, well, this can be used in the calculation of any colligative property. So for any colligative property and for any particle or for any compound that dissolves in water. So it depends, so maybe let's write here, it depends of particles per solvent molecule. All right. So in principle, you can see it in this way, that for every one solvent molecule, there are 2 ions. And for every one solvent molecule, there are 3 ions. And that's what this I introduces. So you can see in the other equations, the I was just a 1. So that's why we didn't write it. But now you have to go back and you need to remind yourself, well, okay, what are all my equations? So we started with vapor pressure. Solvent is equal to I x solvent, vapor pressure of the pure liquid, the change in boiling point equal to I kBp m solute, change in the freezing point is equal to I kFp M solute. And the osmotic pressure, that's also affected, is ICRT. Okay. And you can remember these as is, and hence if you have a molecular compound, so something like chloroform or a protein, or if it says it's a non-electrolyte, then it means the I is just 1. So meaning something that does not split up. Or if there's just one molecule per solvent molecule, then you say I is 1, and then you can just use the formulas as is. But if the I splits up, or meaning the compound splits up into 2 or 3 or 4, then you make the I into whatever the number is that they split up into. Okay. So that's the point of this Van 't Hoff factor. And what is important to remember is that you need to check into how many ever components or ions your solute splits up into, and for how many solute particles there are for your liquid or your solvent. So that's what is I. And once you have that, then the rest remains the same for the rest of the topic. You don't really change anything, you just introduce an I in the calculation of them. All right, so that's it for the colligative properties. So then I'll see you in the next video. Thank you for watching.